Hello, in this video we'll see another form of implication. Let's see this example. We always hear either you do your homework or you will flunk. If we let not A be you do your homework, then you will flunk is statement B. So this statement, either you do your homework, you'll flunk. We could also say, if you do not do your homework, then you will flunk, which negate the A, not A, then you'll flunk. So we have an implication, if then. And double negation of A is just A, meaning is A implies B. So what we're trying to say is that A implies B, an implication, can be written or it is equivalent to not A or B, as we say in these two examples. And to prove that the case is true, we're gonna construct a truth table. So what we start with is that A and B both true, and now true, false, those are all the inputs for A and B, all possible inputs. So either A, B, both true, both false, one true, one false, and vice versa. So as we said earlier, the only time in implication, the implication is false when you break a promise is when true leads to false. Okay, otherwise it is true. So here is the truth value for implied, A implied B, as we've seen before. So now we do the truth value for not A implies B. So what we do first, A and B either both true, true, false, false, true, false, false. We need to negate A, that means opposite to A. And now with the or, as we said before, for all, the only time is false when both are false, otherwise it is true. Now as you could see, the table looks like this for not A or B. What can we conclude, as we stated in the two sentences? That A implies B is equivalent to not A or B. So to find the truth value for a complex, well-formed formula, that means many sentences together, construct its truth table. Build this up from the component part of the well-formed formula, starting with the smallest piece first. For example, if I have this statement, A or not B implies A or B not. So let's see, I break it down, A first, B. So what we could say is you have true, 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 false, 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 and false, true. And now we're gonna negate B, meaning we need false, true, true, and then false. So for the or, A or B not, the only time is false when both are false. Otherwise it's true. And for the or just A or B, again, the only time is false when both are false. Otherwise everything is true. Then we negate the last column which we just did. It's gonna be false, false, true, false. Now what we have? We need the truth value for this statement here, which is A or not B. Let me highlight that. A or not B, right here, implies this. So what we said about implication, the only time is false when true leads to false. True leads to false. So these are gonna be false, and the rest, true leads to true is true, false, false is true. So if I want to stop a minute, this is very complicated statement in a way. How can we reduce it? How can we make it smaller? What is for what entry, what statement is false, false, true, true? If I look carefully, this is exactly not A, because not A is false, false, true, true. And so I could conclude that this statement given here is basically equivalent to not A. So far we dealt with the only A and B, two statements. How about if we have, for example, A, B, C, and D, for example? How many rows we're gonna have? So basically there is a formula for it. So if you have n statement, like in this case we have 4, that means we're gonna have 2 to the power 4, or basically 16 rows of entries, 16 possibilities for A, B, C, D, from changing from true to false. Okay, so letters like P, Q, R, S are used for representing well-formed formula. So sometimes even the well-formed formula, it is like A or B and not C. The whole thing I could call it P, and not A or C, I call this Q, and then I have it even simpler, P implies Q. Now let's talk about tautology and contradiction. When two things are equivalent, so if you do the truth table for the equivalent two statement, you should have everything true. And as simple as when you have A is a statement, A or not A, so let's see. A can be either true or false, and not A is the opposite. So what can we say about A or not A? A or not A? Always true. When a statement, when this always true, we call it tautology. So sometimes you'll be given a statement and they ask you, is this a tautology? Or is this a contradiction? And contradiction basically is when you have everything, every entry is false. For example, again, I just choose simple A and not A. So for the and connective, that's going to be both false. So we have contradiction, okay? And sometimes it's neither. If you have trues and false, and it's neither. So usually tautology is represented by 1, contradiction represented by 0. And that's what we're going to see later when we're dealing with Boolean algebra. Tautological equivalences. So two statement forms are called logical equivalent if and only if, and if you remember, this is equivalence, it's the same as saying they have identical truth value for each possible substitution of the statement for their statement variable. So for example, P and Q, they are equivalent. Either we write it this way or 3 lines parallel like this. So they are equivalent if their truth value is the same. So we have 3 statements. So what does it mean? 2 to the power 3, we're going to need 8 rows, as you see here, 8 rows. So we have true, 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 false, true. So let's construct the truth table for A or B, parentheses or C, and see if this is equivalent to A or B or C, and we just move the parentheses. This is similar to saying 2 plus 3 plus 5 is equivalent to 2 plus 3 plus 5. In algebra, we call this associative property, and it's the same here in logic. And so here is the truth table. So what I'm gonna do, I'm gonna finish up entering all the truth values here. So we take the last column and combine that or with C, and the same with B or C. So I look at B and C, and the only time is false at the last one. Both of them are false. Otherwise, it's true. And now I look at this last column with the C, and we're going to see that the only time is false is the last one. So what can we say? If I call this P and this statement Q, so P equivalent to Q will give me all true, okay? Because they are the same. If the entries are the same, with equivalency meaning the same. So it's gonna be everything true, which is a tautology. And once you have tautology, that means they are equivalent. One more law we're gonna be dealing with here is De Morgan's law. What is De Morgan's law? Is that A or B naught is equivalent to A naught and B naught. So you see that the or become and you distribute the negation. The same with and is going to become or. So let's see if this is really true. So what I did here, I pre-construct the table where you have A and B. You have only A and B, so we have 4 rows. And then we're gonna negate A, and then we negate B. It's the only time it's false is when both of them are false, otherwise it's true. And now we negate the last A or B. And let's look at not A and not B. Here is not A and not B. So for the AND to be true, both of them have to be true. That means I'm looking at this one here. So what can we see? That these two are equivalent. The other one we're going to look at is A and B. So the only time is true, A and B, for A to be true and B to be true. And now I'm going to negate A and B. And then we'll take A naught, which already we have here, and B naught here, and we do an OR for both of them. So since we're dealing with OR, the only time is false when both are false. And now we stop and think, A and B naught is equivalent to A naught or B naught. And this is the Morgan's law. Remember this. We're going to use it later to prove more statements.